So today we're going to talk about how to find power series for functions in general in all kinds of places. As long as those functions are nice, whatever that means, we're not going to talk about it. But the idea is if these functions are nice enough, then their derivatives at a single point tell us everything we need to know to find a power series, a really good approximation, or if it's right if you use an infinite number of terms, in our interval of convergence. So our goal is to be able to find a series representation using differentiation. And so all we're going to need for this is how to take derivatives. So our big idea for how we're going to get approximations for our functions is I want to game a function that is going to match my original function at every derivative at our single point. So let's do all of this is going to be focused at x equals 0. Okay, so let's look at some derivatives of sine. So if f equals sine, then f prime is cosine, f double prime is negative sine, f triple prime is negative cosine again, and the fourth derivative is sine again. And then let's do one more. The fifth derivative is cosine. Okay, so at 0, this gives f of 0 is 0, f prime of 0 is 1, f double prime of 0 is 0, f triple prime, we have negative cosine of 0 is negative 1. The fourth derivative at 0, we're back to sine, so that's 0 again, and the fifth derivative is 1. So I want a function, so create a function, I don't know, let's call it g, so that the derivatives at 0 match. Okay, so to make g of 0, 0, this will make the constant term of 0, 0. So this is this 0. If I want the first derivative to be x, this is going to tell me what the coefficient of x is. So this one will be a 1 here. Okay. So let's check. Let's check what we have so far. So g of 0 is 0 plus 0. G prime of 0 is, so g prime of x is 0 plus 1. So g prime of 0 is 1. That's good. So what should I put here? So I'll have a 0x squared. So that's good. This one's going to take a little bit more thought. So I'll have a minus 1 times x cubed, and this minus 1 is from here. Let's do a different color. Does this work? So if g of 0, if g of x is, this should have been g of x. So we don't need the root 0. X minus x cubed, then g prime is 1 minus 3x squared. G double prime is negative 6x, and g triple prime of x is negative 6. So we don't want minus 1 here, because what I'm wanting to get is minus 1. So I want minus 1. I want to get rid of that 6. I want this to be a minus 1 instead of a minus 6. So what I'll actually use is this. I don't need the 0. X, and then instead of minus 1 here, I'll do minus 1 over 6. Because when I differentiate twice, this 3 is going to turn into a 2 and multiply by 3, and then turn into a 1 and multiply by 2, and that 3 and the 2 will cancel this 6. Okay? So this is to cancel the 3 times 2. And so it turns out the g of x is going to be x minus 1/6 x cubed plus 0x to the fourth, because this is the fourth derivative is 0. And then I'll have a plus 1 over 120x to the fifth. And this number will cancel the 5 times 4 times 3 times 2. Okay, and so if I put this into Desmos, if I can find Desmos, that's not Desmos, go away. Okay, so let's start with sine. And then we said x minus x cubed over 6. So this matches the first the first three derivatives, and then plus x to the fifth over 120. Yeah, and so in this area, that's a good approximation. And so what I did here is I created a function where the derivatives will match. That's the point. Okay, so here's the theorem. If f has a power series representation with a non-zero radius of convergence, then this is a formula that you need to memorize. Okay, so what is this? This is the nth derivative at your center times x minus a to the n over n factorial. And as we were talking about before, this n factorial is there to cancel out what you get from differentiating x minus a to the n. So if I, so why is this? If we differentiate x minus a to the fifth over 5 factorial 5 times, you get 5 times 4 times 3 times 2 times 1 x minus a to the 0 over 5 factorial. And so this 5 factorial cancels the 5 times 4 times 3 times 2 times 1 on the top. So the point of this factorial is, and the way it arises naturally, is from differentiating a bunch of times. So this gives a method for finding a series for any function that we can differentiate without as many fancy tricks. This is a very mechanical process, meaning you can basically follow steps and it just works, as opposed to having to think really hard about like, oh, what method should I be using? This just works. Okay, so here's some guidelines for how to do this. There's a lot of steps here, but the process is fairly simple, except for step 3 and step 4. That's usually the hard part, and then people forget step 5. But basically, we're going to take a function, we're going to differentiate a bunch of times, don't simplify. Once you can guess the next derivative without actually differentiating, then we're going to list off each moving part, make a guess, which has all the right parts, fix your guess, then check if your formula works. Sometimes you're going to have to move off some terms. We'll talk about that later. And then plug in x equals a, and then just write down the answer. Okay, so you can refer back to this as I'm doing it. I will try to refer back to it to make sure all my steps are numbered right, but let's see. Okay, this is the easiest example for finding a power series. So I have f, so let's make a little table. And so this will be the nth derivative of x. Okay, so the 0th term is just my original function. So that's because this is this. Here, this is silly though. What's the first derivative? What's f prime? F prime is e to the x. What's f double prime? It's e to the x. F triple prime. Oh wait, the nth derivative here. So I have all the moving pieces. How many things are changing each time? Nothing is changing, so the nth derivative is e to the x. So this means that the nth derivative is e to the x. So the nth derivative at a, okay, so this was step 1. This is step 2. Step 3 was my guess, and step 4, it was already right, because this one was really simple. Yep. So is f0 of x right? Well, yeah, so this was step 5. Again, this step was a little bit silly. Step 6 is plug in x equals 0. So here, the nth derivative at 0 is e to the 0 is 1. Okay, and step 7 is I literally write this number into my formula. So this will be the sum from n equals 0 to infinity. The nth derivative at 0 is 1 times x minus 0 to the n over n factorial. And this piece is just in the formula. This will always be in all of your Taylor series because it's in the formula. By the way, this theorem here, this is called Taylor's theorem. And what you get from this is a Taylor series. All power series are the Taylor series. Well, if a power series is equal to a function, then it's the Taylor series for that function. And a Maclaurin series, so just a note, A Maclaurin series is a Taylor series centered at 0. So it's this at x equals 0. So we just found the Maclaurin series for e to the x. So when I use that, that's what I mean. So my answer is the sum from n equals 0 to infinity of x to the n over n factorial. And that's the approximation I've been using, or that's the series of polynomials I've been using in Desmos for e to the x. The nice thing here is to do an extra problem, I could do this at x equals 2 because I have the thing that requires me to be able to move is this. I know what the nth derivative at x is. So steps 1 through 5 are all the same. So 1 through 5 have all already been done. So step 6 is I want to plug in the nth derivative at 2. So this will be e squared. So now the answer is sum from n equals 0 to infinity, e squared x minus 2 to the n over n factorial. And here we have both of these approximations made at those 2 points. So the goal is the black approximation is supposed to approximate around 0. The green approximation is supposed to approximate around 2. So they both match the value at 2. When I use just the first derivative, what I get is a tangent line. So this matches the function value and the first derivative. If I do the second one, and then the third one, and then the fourth one, and then the fifth one, and then the sixth one, the seventh one, the eighth one. And so what's happening is they're both converging. And it seems like maybe the black one's a better approximation. The black one's a much better approximation over here, of course. But if I zoom in really far, let's pull back a little bit so we're looking at closer values. So the green one and the red one are basically right on top of each other here, and the black one isn't as good because I'm very close to x equals 2. At x equals 2, let's make this dotted or dashed. Yeah, so at x equals 2, the green one is a phenomenal approximation. And around x equals, even with only 4 terms. This is only 4 terms. And the black one is not a very good approximation at x equals 2. The black one's a good approximation at x equals 0, and the green one's a bad approximation at x equals 0. So basically what happens is as you add terms, both approximations get better, but the green approximation centered at 2 gets better very quickly around 2. See how the green approximation is spot on here, and the black approximation's off by pretty far. Now, as I get more terms, the black approximation pulls in, it gets closer, but the green approximation gets even closer than it was before. So around 2, the green approximation is a better approximation than the black approximation. So see how here it's not quite on, but if I keep going up, yeah, it keeps pulling closer. Yeah, so the green approximation is a really good approximation over here, and it's not as good over here. And the black approximation is good around 0. The green approximation is good around 2. That's the main thing you should take from this. Is moving the center changes where it converges fastest. Okay, so here's a weird example that doesn't generalize but is still instructive. This one is not going to be, this one's just going to be really weird for making the table. So we've already done this table, so I'm going to make my little t-chart of the number derivative and what the derivative is. So the first derivative, the 0th derivative is the original function. First derivative is cosine. Second derivative is negative sine. And then I have cosine, negative cosine. And then I have sine again. And then it repeats. Okay, so here it's actually, here what's the nth derivative? Well, it's hard to tell here, but on this one, what we can do is I can just plug in the nth derivative at 0. So the nth derivative at 0, this is going to give, so 0, 1, 0, negative 1, 0, 1, 0, negative 1, dot, dot, dot. So this is only odds. And so odds have the form 2n plus 1. And then it's going to be alternating. So this will be negative 1 to the n. So what this means is that I will be alternating starting at n equals 0 to infinity, and then I'll only have the odd numbers. So this one's a little bit weird. So don't take this one as an example of how to do other examples, but this is where the sign comes from. So we already saw the x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And it's because of this. This is the 1. This is the minus 1. And then this is this 1. And then you'll have minus x to the 7th over 7 factorial plus dot, dot, dot. Okay. So this is the formula for sine, and this is another one that you can memorize. I think I'll actually give you guys a sheet with these. So this example will be a lot more normal, and will be a lot more instructive. So let's make our table. So the first thing I want to do, step 1, is make a list of my derivatives. Let's just take a bunch. So my original function is 1 over x. My first derivative is negative 1 over x squared. My second derivative will be negative 1 times negative 2 over x cubed. So I'll write this as 1 times 2 over x cubed, so it's positive. My third derivative, so this is times x to the negative 3. So when I differentiate, I'll have negative 1 times 2 times 3 over x to the 4th. And again, this is the, why do I leave it like this? This falls into the don't simplify. Because this pattern will be a lot easier to see if I write it as 1 times 2 times 3 than if I write it as like 2 and then 6 and then 24. Okay, for number 4, this is positive 1 times 2 times 3 times 4 over x to the 5th. And then looking at this, I think the pattern should be the next one will be negative. It'll have a 5 at the end of the top, and it will have an x to the 6th. Okay, so those 3 things should be happening. So if you look, you should just, before you differentiate, before you think about what actually happens from the derivative, just take a guess. So the sign's been changing, so I think the next one should be negative 1 times 2 times 3 times 4. This stays. I'll pick up a 5 from the differentiation, and then I'll have an x to the 6th here. And if I think about what would happen if I differentiated this line, I actually do get this. This makes sense. Okay, and so since I could guess the next one, I'm ready for my formula, and so this will be my guess. Okay, so this was what, step 3? Let's scroll back up. Step 3. Okay, so what? Step 2 is what's my moving parts. So step 2 is I've got 1. I've got alternation. So I need to take care of that. I've got whatever this is. So what is that? This is a factorial. Need to take care of that. And the third moving part is I've got this power on the bottom. So basically I looked, and all that's happening each time is it's alternating. I've got a factorial on the top, and I've got an x to the n. So those things tell me that, well, how do I create alternation? Alternation is negative 1 to the n, always. What is a factorial? Well, it's n factorial. And then I will just write x to the n. And this is not right. What I just wrote is not right, and it is fine. It's fine that it's not right. I'll fix it in a minute. Okay, why is it fine that it's not right? So that's my guess, and then let's just fix. And so what I'll do is I'm going to check by plugging in. Okay, so for n equals 5, this will be my check. So this was step 3. This is step 4. And this is part of step 4 also. If I plug in n equals 5, my formula gives me negative 1 to the 5th, 5 factorial over x to the 5th. And this is good, because it should be negative, that's good. This is good, and this is bad. So this is not n, it's the next number. Instead of being 5, it's 6. So this means cross this one out, and it will be, the next number up is n plus 1. X to the n plus 1. This is my formula. I'm good with that. Okay, step 5 was plug in x equals 1 in this case. So you plug in x equals a was 1. So the nth derivative at a is going to be negative 1 to the n, n factorial over 1 to the n plus 1. So step 6 is plug into the, so check, does the first term fit? Maybe that was step 5. Did I mix those up? The order isn't super important on the last two. Oh, so this was step 6. I wrote 6 all along. Step 5 does, is the 0th derivative at x equal to negative 1 to the 0, 0 factorial over x to the 0, or x to the 1? Yes, so the first term works. This will make more sense on the next example. For number 6, I can just move it over here and act like everything was fine, except this shouldn't have moved. Hey, go back there. No, whoa. Been trying to edit out errors like that, but that was fun enough, and I'm just going to leave it as a little gift to you guys. And then step 7, this step is kind of the most important step, but it is super easy. Literally just plug into the formula. So I've got negative 1 to the n factorial, 1 to the n plus 1. X minus 1, this is important. This is from the center, that's part of the formula, to the n over n factorial. And now cancel. So the n factorials cancel. And this is the sum from, and this is nothing. Negative 1 to the n plus 1 is just 1. So it's just this. As a note, we could have gotten this out of methods we used on the last homework, and I encourage you to try that because it's a lot faster than this, but this is the process. So you take derivatives until you can guess the next one. You list off the things that you have, you guess, you fix your guess, then does it work for the first one? Plug in, and then, so plug in the center and then plug that into the formula. Okay, so here's another example. I'm going to do a power series representation around a equals 2 for natural log of 1 plus x. Okay, so the first thing I'm going to do is I'm going to make a table of derivatives. Okay, so the 0th derivative is natural log of 1 plus x. The first derivative is 1 over 1 plus x. The second derivative, I get nothing from chain rule here because the derivative of 1 plus x is just 1. So I'll have a negative 1 over 1 plus x. For the third one, negative 1 over 1 plus x squared. It's better. And then I'll have negative 1 times negative 2, so 1 times 2 over 1 plus x cubed. For the fourth one, I'll multiply by a negative 3 on the top, so I'll have negative 1 times 2 times 3 over 1 plus x to the fourth. And then here I'll have positive 1 times 2 times 3 times 4 over 1 plus x to the fifth. And this all makes sense, and then basically, hopefully you can guess at this point that the next derivative would be, it's alternating, so it would be negative. So here, let's make my list. So 1, it's alternating. Good. 2, I've got a factorial on the top. And 3, I've got the 1 plus x to the n. If this feels like the last example, that makes sense because the natural log is the integral of 1 over x. So it makes sense that these should be similar. They should have kind of the same pieces. This is on the bottom. Okay, so my guess is going to be, so just get all 3 pieces. It doesn't matter if they're right yet, just get them down. So it's alternating. I've got an n factorial and I have a 1 plus x to the n. It is so much more important to just get something down and fix it than to spend a lot of time thinking about getting it right the first time. Just worry about it in a minute. Okay, so this was step 3. Step 4 here will be my check. So check n equals 5. This is the last one I did. So our projection, our guess says it should be negative 1 to the fifth, 5 factorial over 1 plus x to the fifth. And this says it's negative 5 factorial over 1 plus x to the fifth. So this is great, and these two are wrong this time. So the sign is wrong, so I will change to the actual answer. Oh, fix. Fix is what I said last time. So the fix is going to be -1 to the n plus 1. So the fact that this was wrong means I changed this to the n plus 1. That was no good. And then the fact that this was wrong, this shouldn't have been 5 factorial. In the real thing, it was 4 factorial. So instead of using n, I will use n minus 1. The bottom was right, so I leave it. Okay, so when I saw that the sign was wrong, I changed the alternation from n to n plus 1. That's what changed there. And then when I saw that this was wrong, this was an n factorial. It should have been a 4 when I had a 5. So if I want to plug in 5 and get 4, I have n minus 1 factorial. These two match. Cool. So this is my thing. This is number 4. Step 5 is check if this works for 0. So is the original function -1 to the 0 plus 1 -1 factorial. What does that even mean? 1 plus x to the 0? Is this the same thing as my original function? No. Okay, does it work for n equals 1? So the first derivative is this -1 to the 1 plus 1 0 factorial over 1 plus x to the 1. Is this equal to 1 over 1 plus x? Yes, it is. Okay, so this will mean the sum will start at 1. Okay, and then write first term in the front. Okay, so my sum will start at 1, and I'll write the first term in the front. The sixth step is plug in x equals 2. So I'll need f of 2 because it's off on its own. So the reason I'm doing this one is because it's off on its own. So, and that's why I haven't done it before. So f of 2 is ln of 1 plus 2 is natural log of 3. And then the nth derivative at 2, and here I'll just use my formula. So my formula was this piece. Where'd it go? This. So I'm just using that. So I've got -1 to the n plus 1, n minus 1 factorial over 1 plus 2 to the n. So this is 3 to the n. This is my formula. Okay, so now step 7 is plug in. So I have the sum from n equals 1 to infinity. So why is it 1? Because we said we were going to start our sum at 1. I have -1 to the n plus 1. I've got an n minus 1 factorial on the top. I've got a 3 to the n on the bottom. I have x minus 2 to the n over n factorial. And again, this piece, I wanted that to be a box. Here we go. This is from the formula. And this piece is from here. Okay, so you have one piece that we did all the work for. The rest is from the formula. Now, n minus 1 factorial. Oh, and then this will be the first term. So the first term is, this is f0 x minus 2 to the 0 over 0 factorial is log 3. Okay, so the first term we did off on its own because it didn't fit my pattern. So my answer will be natural log of 3 plus sum from n equals 1 to infinity, -1 to the n plus 1, n minus 1 factorial over n factorial. So this piece and this piece gives me a 1 over n. Let's highlight that. This and this give me an over n. That's where that comes from. And then the 3 to the n just stays. And that's the answer. So this is my Taylor series centered at 2 for natural log of 1 plus x. Okay, now I'm going to do one more example. This is by far the hardest example, so buckle up. Okay, so we want a power series representation around a equals 4 for square root of x. Here we go. Let's do it. Let's do it. Everybody excited? The hard thing here is just the pattern is going to be a little bit less pleasant than what we've been doing before. So here, instead of writing this as square root of x, I'll write this as x to the 1/2. Okay, my first derivative is going to be 1/2 x to the negative 1/2. My second derivative, I'll have 1/2 times negative 1/2, so it'll be negative 1/2 times 1/2 times x to the negative 3/2. Okay, 3. It'll be positive again, so I'll have 1/2 times 1/2 times 3/2, x to the negative 5/2. And again, I'm not simplifying. The place where you can start simplifying is when you understand where something is coming from. So now that I see that I have 1 2 here, 2 2's here, 3 2's here, and that this is going to create my fourth 2, that means that I can go ahead and start writing this as 2 to the 4. Okay, so the denominator here will be 2 to the 4. I'm confident that I'll get a 2 every time. The other thing is I know it'll be negative, and then the top will be 1 times 3 times 5. And I dropped the first one because I don't think it matters. To be honest, the second one doesn't really matter either, but we'll worry about it depending on how you feel about things. The next one, it'll be positive again. Then I'll have 1 times 3 times 5 times 7 over 2 to the 5th. Okay, now you should stop and take a second and guess the next term on your own without taking the derivative. Just look at it, think about it, see if you can guess the right next term. So I think it should be negative 1 times 3 times 5 times 7, and I'll tack on a 9 this time, 2 to the 6th, x to the negative 11 over 2. And what I would think is the next one would have 11 at the end, and then the next one would have a 13, and the next one would have a 15. Okay, so now let's, this was our step 1. Step 2, let's take our inventory. So how many things are changing? So if you stop and think about it for a little bit, I claim there should be 4. There are 4 things changing. I just want you to know that it's sitting alone in my office. I just lifted up 4 fingers as if you guys could see me. So that's great. So first we've got that alternation that seems to keep happening. Alternation. 2, we've got whatever this thing is. It's a running product with an odd number at the end. Okay, and then I've got a 2 to the n in the denominator. And then I've got an x to the negative odd number over 2. Okay, so let's put all those together. My guess for n would be just write the parts. We'll worry about it later. Don't worry if it's right. Just get it something down. We have a negative 1 to the n. I've got 1 times 3 times 5 up to an odd number. I'm just going to write 2n plus 1. I've got 2 to the n in the denominator, and then I've got x. How do I create an odd? It's negative 2n plus 1 over 2. Okay, this is my guess. So 4 will be check it. So if I plug in n equals 6, then this says I'll have negative 1 to the 6th, 1 times 3 times 5, dot, dot, dot. 2 times 6 plus 1 is 13. 2 to the 6th, and then I have x to the negative, that's still 13 over 2. And is this right? So this is wrong. This is right. 2 to the 6th is right, that's good. This is wrong, and this is wrong. So for this pink one, we had 13, and we want 9. So this was 2n plus 1, so scratch that. Let's try 2n minus 1. That would give me 11. Scratch that. Tick off one more. The one before 2n minus 1 would be 2n minus 3. Okay, so my right answer for this thing will be 2n minus 3. That will give me a 9 there. And then for this one, using the things I just made, this one said this should be 2n minus 1. For this. Okay? So, and then, so I need to fix everything. So my fix will be, instead of negative 1 to the n, that was wrong. This will be negative 1 to the n plus 1. There's only 2 options for your alternation. So as soon as it's wrong, just switch to n plus 1. The top here will be 1 times 3 times 5 up until 2n minus 3. I have x to the negative 2n. We said this was negative 2n minus 1 over 2, and the denominator we said was already right. That is indeed 2 to the n. Bada bing, bada boom. Okay, step 5 is I need to check n equals 0. So if I plug in n equals 0, this gives me negative 1 to the 1, 1 times 3 times 5 times 2 times 0 minus 3. Oh, I need a dot, dot, dot. Does that make sense? No. Ooh, don't like that. So n equals 0 isn't going to work. Don't even need to finish. This one goes from 1. So it starts at 1 and it goes up to negative 1? No, don't like that. If I plug in n equals 2, then this gives me negative 1 cubed times 1 up to 1. So this just means just a 1 on the top, and this is okay. Okay, so I need to pull off, so start at n equals 2, and then pull off 2 terms. Okay, step 6 is plug in, and let's go back up to the top, x equals 4, because a is 4. So we'll have negative 1 to the n plus 1, 1 times 3 times 5, dot, 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 2n minus 3. I have 4 to the negative 2n minus 1 over 2, all over 2 to the n. Okay, so this is the nth derivative at 4. Okay, this one I can fix a little bit. So this minus power means I can move to the bottom. So I'll have negative 1 to the n plus 1, 1 times 3 times 5. This is actually called a semi-factorial. You don't need to know that, but it's fun. And then this over 2, this means square root. So this will be negative 1 to the n plus 1, 1 times 3 times 5, dot, 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 2n minus 3. And then I have 2 to the n and 2 to the 2n minus 1. So this 2 being a square root means this is a 2 now. Okay, so first 2 terms. I needed the first 2 terms. This is f of 4 times x minus 4 to the n, or x minus 4 to the 0 over 0 factorial is square root of 4 is 2. My second term is f prime of 4 times x minus 4 to the 1 over 1 factorial. And so this will be 1 over 2 square root of x, because that's the derivative. So 1 over 2 square root of x is the derivative. So I have 1 over 2 square root of 4 times x minus 4 over 1 factorial. So this is 1/4 x minus 4. So my answer will be the first term plus the second term plus my sum. Okay, so 2 plus 1/4 x minus 4. And why am I doing all of this? Again, because we decided that the first 2 terms don't fit my pattern. These 2 terms right at the beginning, these did not fit into my falling factorial, like the 1 times 3 times 5 thing. That didn't work, so I pulled them off. And then I have the sum starting at n equals 2. I have negative 1 to the n plus 1, 1 times 3 times 5, dot, 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 2n minus 3 over 2 to the n times 2 to the 2n minus 1. This was fn of 4. And I have x minus 4 to the n over n factorial. And this piece, again, is just from the formula. And that's the answer. This is by far the hardest type of problem that we would ever see for this. This one was a doozy. So have a great day, guys.